Welcome to my fifth tutorial on statistical thinking, titled Making Statistical Decisions with Confidence Intervals. As should be clear by now, when conducting research, ideally we want to select a sample of quality data from a population of interest. A population we clearly define, like the population of individuals with high cholesterol. From our sample of data, we calculate a sample statistic like the sample mean cholesterol level of patients on a drug for lowering cholesterol. The sample statistic is an estimate of some unknown truth in the population, known as the population parameter. In this example, that value would be the population mean cholesterol level of all individuals in the population, if everyone in the population were to take the drug for lowering their cholesterol. We will use the sample mean, the standard error of the sample mean, and the result of the central limit theorem, the sampling distribution, to make statistical decisions regarding the value of the unknown population mean. The first approach we will use to making statistical decisions regarding the value of the population parameter of interest is called the confidence interval. We can say with a certain degree of reliability, most commonly being 95%, that our population parameter is one of a range of plausible values within the interval we will construct. For this approach to be valid, it is very important that the sample data collected adheres to the necessary assumptions and conditions for valid analysis. If our data is of good quality, we can assume that our sample statistic is one out of a range of possible sample statistics distributed under the normal distribution, centered at the unknown population parameter. We will use a simple analogy to help us understand what is a confidence interval and how it is constructed. Imagine that the measurement line drawn below the normal distribution in the figure shown is a long straight stretch of the Mississippi River. The normal sampling distribution drawn above the line is a mountain not far from the riverside. One particular day, a fisherman in his boat, the sample statistic, is riding along this stretch of the river, hoping to capture what is known as the great fish of the Mississippi River, the population parameter. At this particular time of year, the great fish is known to be sleeping in the part of the river directly beneath the mountain peak. The problem the fisherman has is that with large trees covering the river bank, he can't see the mountain and thus his exact location in relation to the great fish. However, he knows his nets can extend 2 standard errors in both directions from his location. Therefore, he is highly confident that he will catch the fish within his nets, because there is a 95% chance or probability that his boat is within 2 standard errors of where the fish lies sleeping. So what he decides to do is cast his nets 2 standard errors in both directions, up and down the river. He knows that if his boat is within 2 standard errors of the fish, between the grey shaded areas in the figure shown, then the fish will get captured somewhere in his nets. If his boat is more than 2 standard errors away from the fish, in the grey shaded areas in the figure shown, he won't capture the fish with his nets. There's a 5% chance or probability of this happening. By fishing in this way, the fisherman can be 95% confident that he will catch the fish within his nets. The 95%, or 0.95, is a probability value, known as the confidence level. From our point of view, we know that if this process could be repeated over and over, the fisherman will be within 2 standard errors of the great fish 95% of the time, meaning that 95% of the time he would capture the fish somewhere within his nets. In other words, when we select a random sample of a particular size, we know from the result of the central limit theorem that our sample statistic is one of a range of possible sample statistics normally distributed around the population parameter. Consequently, there is a 95% probability that our sample statistic is within 2 standard errors of the population parameter. By subtracting and adding 2 standard errors to and from our sample statistic, we can calculate lower and upper limits for an interval of plausible values for the population parameter. As a result, we can say that we are 95% confident that the population parameter is within that interval. The 95% probability, our confidence level, refers to the confidence we have in the process. Imagine selecting numerous random samples of the same size and constructing a confidence interval based on each sample. As we increase the number of times we repeat this process, the percentage of the confidence intervals containing the population parameter will approach 95%. The figure shown illustrates this point, representing 20 confidence intervals based on the same sample size. The blue dots represent the sample means, and the horizontal black lines represent the width of the confidence intervals. The vertical black line represents the population mean. The upper and lower limits of the confidence intervals will differ from sample to sample, and we expect 19 out of every 20 95% confidence intervals to contain the population parameter. We expect only 1 in 20 or 5% of confidence intervals constructed this way to not contain the population parameter. Again, it should be repeated that the level of confidence we have in our confidence interval also depends on the quality of the data used to construct it. We will look at a simple example of constructing a confidence interval. The data used is the cholesterol levels of heart disease patients in the Cleveland Clinic, taken from a website called kaggle.com that provides a range of different types of data sets for you to download and analyze. Again, we will question the quality of the data for valid statistical analysis, which I do in depth for the examples presented in my book. For this tutorial, however, I simply want to show you how a confidence interval is constructed based on real-world data and explain what it means. From the sample data, we calculate the sample mean and the sample standard deviation. The standard deviation, along with the sample size, can be used to calculate the standard error of the sample mean. In this example, the standard error is the sample standard deviation of 51.8 divided by the square root of the sample size equal to 303 patients. The resulting standard error is equal to 2.98. The standard error is multiplied by 2, which is equal to 5.96. This value is taken away from the sample mean of 246.3, resulting in 240.34, the lower limit of the confidence interval. Then we add 5.96 to the sample mean, resulting in the upper limit of the confidence interval equal to 252.26. The confidence interval means is that we are 95% confident that the population mean cholesterol level lies somewhere between 240.34 and 252.26. The population is all heart disease patients that attend the Cleveland Clinic. Finally, we'll look at a media example to try and ingrain this statistical concept. The range of plausible values within the confidence interval can be thought of as a probability map. A good comparative example is the probability map used for predicting the path of hurricanes. In September 2017, the center of the probability map projecting the path for Hurricane Irma indicated that Miami, Florida, would get a direct hit. However, as the article in the New York Times titled Irma Shifting Forecasts, It's All a Matter of Probability, pointed out, quote, many people trying to use the forecast like those provided by the National Hurricane Center, however, do not fully understand the cone of probability and focus instead on the line that runs down the middle, taking it as an accurate prediction of the storm's path. End quote. The line that runs through the middle of the probability map, or cone of probability for Hurricane Irma, is analogous to our sample mean in the middle of our confidence interval. It turned out that the center of the storm went somewhat west of Miami, hitting the Florida Keys, but was within the area covered by the probability map. This is analogous to our population mean being somewhat to the left of our sample mean within our confidence interval. In this tutorial, you learned one approach to making statistical decisions about a population parameter of interest. You gained a conceptual understanding of what a confidence interval means and how it is constructed. In my book, I explain how to reason with confidence intervals for more real-world scenarios, for example, comparing the mean cholesterol levels for patients on 2 different treatments. We calculate and reason with a confidence interval for the population mean difference, also known as the population effect size. In our next tutorial, we take a different but much used approach for making statistical decisions about the population parameter of interest, known as hypothesis testing.